Hi everyone, I'm Bradwell, and let's look at Newton's second law. In equation form, Newton's second law says F equals ma. Now, this equation says the F, which is the net force on a system, where a system could just be a block or a projectile or just anything you're examining. So the net force on a system will equal the mass of that system or something you're observing times its acceleration. This does not mean mass times acceleration will itself be a force. It's just saying when you add up all the forces on a system, it'll equal mass times acceleration. So let's look at some classic examples of Newton's second law. Let's solve some problems. So let's say we have a block of mass M, big M, on the ground, and there's friction here between the ground and the block. And there's also a tinier block with mass little m on top of this big block, and there's friction between these two blocks. And let's say we push it with the force of capital F. And the question asks, well, my question is, what force causes this tiny block to accelerate? Because logically, when you press on these two blocks like that, you'll know just from experience that these two will slide together. So that means there's a force that's going to be acting on this top block, or else it would just fall off the big one, the big block. So the question is, what force acts on this little block that causes it to accelerate along with this big M block? So let's look at this small block system. The little m, the mass of little m block system. Let's look at that. Well, first, let's say this is the block of little m. Well, we're going to draw a free body diagram, and what that is just you draw all the forces on this block, and then try to use Newton's second law to explain what's happening to it. So we know that there's going to be a force pointing downwards due to its weight, due to Earth's gravitational pull on this block. So we call this force mg, the mass times g, and then since the block isn't moving up or down, it's only moving laterally, we know there's going to be an equal and opposite force pointing upwards. Now, where does that force come from? It comes from the normal force produced on this upper block by the lower block. So we call this the normal force. A lot of times we'll just say capital N. The normal force will show up a lot. And then we know, I said there's friction between these two blocks. Now, friction is also a force. And we know, since the block is moving this way along with the lower block, that means this upper block, for this upper block, the friction force will be going this way, since this is the only lateral x direction force on the upper block. So we call F sub F, this little tiny, here let me write it bigger. This little tiny f is for friction. So I drew all the forces on it, and Newton's second law says F equals ma. So that means the net force on this block will equal this block's mass times its acceleration. So that means since the net force is when you add up all the force vectors on that system. So this force and this force will cancel out. So that means the only force, or the net force on this block, is just this right here. So that means the net force, or the sum of all the forces, equals MA. So, and then if we had more numbers and constants, we could solve this problem for F or M ray, or like the force of friction on it. But our original problem was, what is causing this block to move? It's not the normal force, it's not the mg force, because both of which are canceled out by the other. So that means the force of friction is causing this upper block to move. Not this force we're pushing the big block with. That does not directly cause this upper block to move. It's the force of friction. Let's look at another problem. Let's say we have three blocks side by side by side. The small block is 1 kilogram. This second block is 2 kilograms. And this last one is 3 kilograms. And we push horizontally on this first block with the force of, let's say 6 newtons. So I'm introducing some actual numbers here. Now the problem asks, what is the force between these two blocks, and what is the force between these two blocks? So now let's do Newton's second law for this 3-block system. So I'm going to look at these 3 blocks all together first. I'll just draw it like this. So these are the 3 blocks. And also assume there's no friction between the blocks and the ground in this scenario. So if I were to draw a free body diagram, it would look like this for this system, this 3-block system. There would be this force of 6 newtons. And this mass altogether is 1 plus 2 plus 3. So the mass will equal 6 kilograms. So that means for this system, if I write F equals ma, I'm going to get the net force on it is just 6 newtons. Oh, well, there's also, here, let me say, there's also an mg, the mass of this whole system due to gravity, and then there's a normal force from the ground. But these forces cancel out, so the net force on it will be only due to this. So the net force, F, will equal its mass times its acceleration, and the net force on it is 6 newtons in the x direction. Sorry. 6 newtons equals 6 kilograms times A. And since 1 newton equals 1 kilogram meter per second squared, that means A equals 1 meter per second squared. So now we know the acceleration of the whole thing. And then now let's look at this 1 kilogram block. So I'll say A equals 1 meter per second squared. Let's look at this 1 kilogram block. And let's draw a free body diagram on it. There's mg, like I said, and there's a normal force. But like I said, since it's not moving in the y direction, up or down, the net force in the y direction will cancel out and equal 0. So now there's a 6 newtons force And then there's a normal force on block 1 produced by block 2. And we also know, since this block will be moving in this direction at 1 meter per second squared, this vector will be longer, which represents greater magnitude than this one right here. Let's make that shorter. And let's call it the force of block 2 on block 1. So that means the net force on this block will equal 6 minus this force of block 2 on block 1. That's just the net force equals NA. The mass of the system we're observing is just this 1 kilogram block, so it equals N times acceleration. Now acceleration of this 1 kilogram block is going to be acceleration of this whole thing, so it's 1 meter per second squared. So this A will just be 1 meter per second squared. So that means we know 6 minus this F of 2 on 1 equals 1 Newton. This is 1 Newton. So that means this 6 Newtons. Sorry. So that means the force of 2 on 1 is going to be 5 Newtons. Which also means, since those two blocks are always staying together, the force of 2 on 1 will equal the force of 1 on 2, which is also 5 Newtons. So now let's look at, we solved for that. Now let's look at let's solve for the normal force between these two blocks. If we can draw a free body diagram for this one or this block. I'll choose block 3 because there aren't normal forces in both directions as there are on block 2. So let's say block 3, I'll draw it kind of big. Let's draw a free body diagram on it. It has mass, or it has weight, so mg. Has a normal force, but we're not really worried about that since they cancel out. So it has a force. Now this force is the force of block 2 on block 3. And that's all the forces on there. So the net force equals ma. That's what Newton's second law says. So that means the net force is just this force right here. F of 2 on 3 will equal the mass of this system we're observing, 3 kilograms, times the acceleration of that block, which is just 1 meters per second squared. So that means the force of 2 on 3 is just going to be equal 3 newtons.